I'm reviewing a practice chi-squared problem, one that gives a lot of AP Bio students and other students fits because it deals with something called the null hypothesis, okay? And it also deals with probability of your statement. And a lot of people get lost what this all means. The bottom line is a chi-squared statistical analysis is one way of looking to see how well numbers that are observed are they close enough to something that we expect? Now, if you think about flipping a coin, we know that there's the head side and there's the tail side, and that we know that we can either have heads or we can have tails. And if you were to flip this over, okay, you'd probably get 50% expected heads and 50% expected tails. However, if you were to flip a coin 3 times, you might get 3 heads in a row, or you might get 3 tails in a row, or you might get something in between. Okay, the point being is that we may get results that are not what we expect in the observable range because of chance events. Now, a chance event means that, yeah, you can have 10 tosses of a coin and you may not get 5 heads and 5 tails. You may get 7 heads and 3 tails, or some number other than 50%. And what we do in a chi-squared is see if, in fact, what we see or observe is due to chance events alone. Now, we're talking about a biological problem when it comes to, let's say, Mendelian genetics. In this case, we're crossing plants. The chance event is that one gamete, okay, and another gamete coming together, okay, the chance of a certain gamete with a certain allele mating or making a zygote with another allele is a total chance event. So it's like flipping a coin. Now we know if we have billions upon billions of chance events, they should work out to be about what we expect if it's only chance. So there's always going to be differences in the observable compared to what we expect because of these chance events. However, what if it's a non-chance event? What if there really is a difference beyond the chance? That is what the chi-squared tests. It tests to see, is there something besides chance, besides just how you roll the dice or flip the coin? Is there something else involved? In the case of the coin, it might be the coin is fixed. Maybe there's a heavier side that makes it flip one way or the other. Or in the case of a scientific study, maybe there's another variable causing the results, not the one you're studying. So we got to look at the observed, what we get, okay, compared to what we expect. And if that difference is based on chance alone, the chi-squared test will tell us that. So what we do is we set up a null hypothesis. In that null hypothesis, we state our test, so to speak, of the chance. So in a case of flipping the coin, I will say there's a 50% chance that we'll have heads or tails. That is my null hypothesis. My null hypothesis is a null or a zero hypothesis because it is taking out all the other possibilities. Sometimes people say it's the devil's advocate because you're saying there is no difference between these two things. Zero difference. That's where the null comes in. Okay, why is there no difference? There's no difference because any difference we have is due to just chance events of flipping the coin. Again, I've talked about this often. People, families sometimes have a bunch of boys and no girls. These are independent chance events. Yeah, there's a 50% chance of having a boy and girl. Yet, okay, we'll have families that have a bunch of girls and no boys. We do not have oftentimes, and you'll see that more often enough. But if you were to have 1,000 or 1,000,000 siblings or kids in your family, they will work eventually out. So this null hypothesis, again, is about the idea that nothing, null is the difference between observed and expected because any difference is due to those random chance events. Again, if we test this hypothesis and we find it not to be correct, that there's more difference here beyond chance, then we can just say something else is occurring. And how do we do that? Well, we do the chi-squared analysis, and that gives us a probability or a p-value. And a p-value measures, okay, measures how strong the null hypothesis is. If I have a 100% p-value, or very high, in this case, extremely high, that would mean that the null hypothesis is supported. So understand the p-value is the support for the null hypothesis, or the lack of support. If you get a low p-value, a low probability, that would mean that you have a what? A low probability of supporting this hypothesis, which means we reject it and something other than chance is affecting it. Make sure you understand this. We're going to do a chi-square based on our null hypothesis, stating that the only difference between observed and our expected is due to chance events, because you can't eyeball it to know. All right, besides that hurts your eyes. But the point being, you have to know what's the cutoff between a chance event differing my expected from my observed, or there is a big difference. That's where the statistical test gives us. And what it does is it gives me a p-value that gives me the strength of the null hypothesis. If my p-value works out to be high, that means that I can definitely understand there's a great chance that null hypothesis can be supported, and there really is no difference, even though the numbers look different. If my p-value is low, I have very low support for the null hypothesis, and I can say that the hypothesis is not supported. I can reject it in something other than chance. Now, what gives us these probabilities or level of strength of null hypothesis? It's that chi-squared value, that statistical test we're going to do. So that's what this is about. So let's clean this up because I can, and I know it bothers people. All right. All right, so I got this cleaned up, and now we're going to do the problem. I got a certain species of a flowering plant. The red allele is dominant to the white allele, that's little r. A student performed a cross between a red flowering plant and a white flowering plant. When planted, okay, and let's stop here for a second. What do we have? A student performed a cross between a red flowering plant. Now, a red plant, I know I'm writing in blue, so it's kind of silly. A red plant was crossed, okay, with a white plant, white flowered plant. I should say a red flowering plant with a white. Now the white had to come from the what? The recessive allele, and we should all know to get the white phenotype, it must be what? It must be little r, homozygous recessive. That's the only way to get the white. Now the red plant, we don't know if it's homozygous dominant or what? Heterozygous. That is our question. Which one is it? Okay, so for this question, they want to understand, they want to test to see whether in fact the outcome of this parental cross, which by the way will give us F1, okay, which is the first generation, if we can look at the babies, the zygotes, or in this case, the plants that grow from the seeds, whether these outcomes will support the idea that we have a what? A heterozygous mom or dad. So the point of this entire statistical problem or biological problem is to see, in fact, if we can find evidence to support the fact that the mother or father or one of the parents is heterozygous. So our null hypothesis, okay, is going to be that there is what? That the plant is heterozygous. Now, that's not a very good null hypothesis. What we're going to state in our null hypothesis is that the outcome from the cross is going to be consistent with this. Now, before I write the null hypothesis, let's see what the outcomes are. We have 148 seeds that are made, but what do we have here? We have 88 that are red flowers, and we have 60 plants that are white flowers. Now what are we looking at here? Well, these are my outcomes. Now, would this phenotype, remember it's phenotype because I don't know the genotype or red. Red can be two combinations. Is this consistent if the plant was heterozygous? Well, let's see. Let's first do a cross. Let's do a Punnett square, and let's pretend that it is heterozygous, and let's cross it with the homozygous recessive. And what we're going to get is big R, little r, little r, little r, and then big R, and then little r, just a little Punnett square here to understand what I should expect, hey, sounds familiar, if in fact it's heterozygous. So looking at my results, clearly, party people, okay, 50% of my phenotypes should be white flowers, and I would write that in white, but that wouldn't work out, and then 50% will be red. So that's my expected. So here is my observed, and my expected should be 50%. Now, because I have 148 flowers, 50% of that is what? 74. Okay? So I expect to have 74 flowers. Now, eyeballing this looks, what? Pretty similar, but how similar? How close are these values? So my null hypothesis here is that there is what? There is no difference between the observed and the expected. Or in this case, I should expect that the red flowers and the white flowers happen 50% of the time. So the null hypothesis is, in this case that I'm testing against, because there is, I'm going to say there's no difference, that the expected phenotype, so just put pH, okay, will be 50% what? Red and 50% white. That is my null hypothesis. That the expected, I should say the expected will be 50% red and 50% white. That is my null hypothesis that I'm going to test. And if you think it back to what I just talked about, I'm saying that these should be close enough to show that there's no difference. And looking at this, it seems like they're pretty close, but again, you can't eyeball it. It hurts, but you got to use a statistical test. So my null hypothesis here, understand this, is that there is no difference between the two. Null, there's no difference, because we are saying that the expected phenotypes should be 50% white and 50% red. Now, it's not always going to be 50%. If I did a different cross that I was testing for, it could be a 3-to-1 cross if it was. And I could set my expected to be 75% and 25. So don't fall in love with the idea. Don't be a robot and think it's always going to be 50%. The idea here is that our expected is matching what we would get if it's what? Heterozygous. So if you look at the problem, calculate the chi-squared value for the null hypothesis that the red flower was heterozygous. For it to be heterozygous in my Punnett square, I have to get 50% of each of these. So my null hypothesis, what I expect, if there really is no difference, null would be 50% in this case. And now I'm ready to do my math. So we need to do the math, the chi-squared, and from your reference table, okay, you should know that the chi-squared formula is equal to, not good at making a chi-squared, but the summation of the observed minus the expected squared over the expected. So my friends in biology, I know I said that right, that's what that's the chi-squared formula. And we're going to use that to get a chi-squared value and then put that into a table. Okay, so sometimes it's helpful to have your table here. We have our observed, our expected, okay, our O minus E squared maybe, and we'll do that. So what do we have here? We have 88 red and we have 60 white. And doing our mathematicals, that's our observed, so I guess I should have put the O there. Okay, and we'll just work from there. And then what's our expected? Well, we're going to minus that from our expected. Our expected is to be 74. That would be half because of what we just talked about. So let's go find those values. We put them in our calculator. And okay, so I get 14. And I'm going to square that. And I get 196. Remember, I have to divide it by what? E, which is the expected, which is 74. So I guess my other table should be 0 minus E squared over E. Okay. And you don't have to have the table, but sometimes it makes it nice and organized for you. And so I'm going to do 196 divided by the expected, and that's 74. And I get 2.65 for there. 2.65. Okay, now I'll do 60 minus 74 for the other allele or trait there. And of course I get negative 14. And you can see what's going to happen here. That's going to make it positive. That's why they square that. That's 196 over the expected, which is still 74. And that's going to give me 2.65. Now don't forget this. It's easy to mess this up. There's a summation sign there. Okay, what does that mean? You sum all the individual, okay, components here. You had two phenotypes. So we have to add these things together. So clearly 2.65 plus 2.65 gives me about 5.30. Good enough. So that is my answer here, 5.30. That is what's equal to my chi-squared. Now what do I do with that? Remember, this is a statistical test to see if, in fact, these expected values and these observed differ only by chance events, and that they are essentially 50% when you take away the chance events. Well, now I have to go to a chi-squared table to look at that. So we go to a chi-squared table. We have one in our reference table. Let's go there. So our value is 5.3, and I know some people said, well, okay, degrees of freedom, what's that? Well, we had two phenotypes we were testing. There's either going to be red or white. So if you know you have white, okay, then you have to have red. So if you have only two different choices, okay, once you know one choice, you know the other because there's only two choices. So we would say the degrees of freedom are only one here. You always subtract the number of the things, the categories, you subtract minus one here. So, and again, the reason why that works is if you have red or white, you only have one degree of freedom. It's red or white. Once you have the red, you have the white. If you have the white, you have the red. So you take the number of categories and you minus one. And we look at our 5.3, and if you notice, it's greater than 3.84. So it fits in between here, or it's bigger than 0.05. I mean, what's so important about 0.05? Well, statisticians or mathematicians or probability experts, whatever you want to call them, they're more comfortable by saying if something is only 5% probability, 0.05 is 5%, that's a very low probability to support the null hypothesis. So anything that's 0.05% or lower in probability or p-values has such a low support for the null hypothesis, it's a point where we can reject. So anything that is lower than 0.05% p-value, which means a larger chi-squared, remember the bigger this value, the lower this goes, that's our basic Mason-Dixon line. So our value is chi-squared is 5.3, so that's bigger. Notice 0.01 is bigger. So if you got like a 10, it's even better. So bigger the chi-squared, the lower the p-value. So we have a number bigger than 3.84. So that means the p-value is actually less than 0.05. So the cutoff to accept the null hypothesis is 0.05. We've exceeded that, something lower than that. So let's go back to the problem. So our p-value, okay, is less than 0.05. And we reject the null hypothesis here. Why? We have a low probability that supports the null hypothesis. What's the null hypothesis? That we should get what? 50% red and 50% white flowers. Okay? With a low p-value, what this tells me is that there's such low support for the null hypothesis that something besides chance is making these numbers differ. And what that something other than chance could be is that it's not big R, little r. It could be what? R and R. So something besides chance is making these different. So therefore, it is not heterozygous. What is it exactly? Don't know, but we know that it looks like, it appears that there's not enough probability for that to be heterozygous, according to statisticians. So some other factor is playing, and it could be another genotype, or it could be chromosomes that are linked where the alleles are on the same chromosome, so that you're not going to have this independent assortment, or that you would get from Mendelian genetics. Okay, I hope you can see that. All right, hope that helped.